in A. And also you can replace j by I in B, meaning that you get basis in these ways. Okay, so that's the exchange axiom for the basis. And so as you see, I'm identifying the matrices, the matroid with the set of bases here. So as an example, if I take my ground set E to be 1, 2, 3, 4, one of the matroid is this one, this set of bases. So in other words, this set satisfies the exchange axiom. If you take two sets here, A and B, then you will have this property. Okay, now I want to present another way to look at this data. So sometimes it's going to be useful to, instead of looking at the set of bases as some sets, maybe I want to see them as, you know, points like vectors, 0, 1 vectors. You know, I'm just looking at the incidence vector of these sets. So, all right, so let's take this perspective that's, in other words, I'm looking at my bases, and now I think of them as points in 0, 1 to the E. And how will I know that this form a matroid? Well, the characterization is that if you look at the convex hull of these points, so this is going to give you a polytope inside the unit cube. All the edges have to be of the form AI, EI minus EJ for some elements IJ of the ground set. Here an EJ means the canonical, the elements of the canonical basis. So EI is the point with coordinates 0, 0, 0, and 1 in the ith coordinate. Okay, so here there is this correspondence between, you know, a set of sets and here a basis. If I do an example, you know, in terms of on the ground set 1, 2, 3, I could look at my matroid as this set of bases 1, 2, 2, 3, and 1, 3. But also maybe I can associate to that a polytope. I'm going to take the points on the vertices of the cube that correspond to this, that encode this basis. So I will have the point 1, 1, 0, the point 1, 0, 1, the point 0, 1, 1. And I'm taking the convex hull of that. I'm going to get a polytope. And this polytope, the basis polytope of my matroid, has this property that all the edges are along these directions. And that's actually a characterization. So, all right. So that's a more geometric perspective. And a third way to look at matroids or define matroids is in terms of the rank function. So here, you know, in terms of the polytope, you know, we are looking here as we are kind of characterizing the polytope in terms of the edges, but we could also characterize it in terms of the facets. So we can think of this as this, another characterization of these polytopes is as follows. We are going to have a polytope in RE such that all the facets are given by inequalities of this type. Some for a set, for sets S, for any given set S, I would have an inequality of the form sum of the coordinate xi for I in S is less than a certain value, f of S. And for the total sum, it's an equality. So the sum of xi for the sum of coordinates is equal to a given value, the rank. And okay, so if I take this perspective, I'm going to get so I'm looking at matroids as polytopes, and these polytopes are the polytopes that have this form where f is a submodular function, a positive non-negative submodular function, such that the value on singletons is 0 or 1. So just as a reminder, what is a submodular function? It's on the Boolean lattice. It's a function from the sets of subsets of E to the integers here, such that for any sets S and T, we have the following inequality. So the value f of S plus f of T is greater or equal to the value of f of S union T and f of S intersection T. And this is with the convention. We take always the convention that f of the empty set is 0 for submodular functions. So actually, the function f here is uniquely determined by the matroid, by this polytop. If we impose that it's a submodular function, because if you look at these inequalities that define the polytop, maybe some of them are not necessary. They might you could maybe get away with not defining some of them. But actually, if you want to be submodular, it means that each of these hyperplanes is going to touch actually your polytop. You have no choice. And that's going to define uniquely your rank function. And that's okay. That's another way of describing matrix. So I think that okay. So this is just a normal background on matrices. Now I want to describe polymatrices. So it's a generalization of matrices. So let's see how these different things get replaced. So in terms of basis, a polymatroid on the ground set E is going to be a finite set P of points in Z to the E. So you could think of them as multisets of elements of E, or you could think of these elements P as replacing the indicator vector, the 0, 1 vector. Now it's in Z to D. All right, and how do we update our exchange axiom here? So we will have this finite set of element in Z to the E, and they have to satisfy, we call them bases, and they have to satisfy this exchange axiom that says the following. If you have two bases, A and B, and an I in E such that the coordinate of A, the ith coordinate of A is greater than the ith coordinate of B, then you can take A and decrease its I coordinate and increase another coordinate and stay within your set of bases. So precisely the condition says there should exist a J such that the J's coordinate of B is greater than the J's coordinate of A. And when you take A and increase the J's coordinate and decrease the ith coordinate, you stay in P. And for B, you can simultaneously do that, and for B, you can increase I, decrease J, and stay in P.
Olivier, there is a question by Meza Perez that in definition 1 must elements A and B be different?
M is void when A is equal to B because there would not be any I that does that. Does that answer the question?
Meza, did it answer your question?
So you can take A and B. You can take A different from B here. What this says, let's compare it to the definition of the exchange axiom for matrices. For matrices, what we say is that if you have two bases that are different, then you can take A and get closer to B while staying within a set of bases. And by closer meaning you can take an element take out an element that was not in B and replace it by an element that was in B. And then and stay in a basis. And you can repeat that up until the time you are transformed into B. Same thing happened here, but at the level of coordinates this time. Each time that you have a coordinates that is different from between two bases A and B, you can make a tiny change of coordinate, increase one and decrease one in the direction of this B, and stay within your polymetry. One consequence of the exchange axiom is that the sum of coordinates is constant. It's going to be the constant of your polymetry. In the same way as the number of elements in basis of matrix is constant. Okay, any other question?
Yes, do you need both A plus EJ minus EI and B plus EI minus EJ in P? I mean, in the matroid case, you don't need both.
Yeah, this is a strong form of the exchange axiom. So the exchange axiom, you can write it in strong or weak form. You get the same. You can prove that the weak form implies the strong form in matrix.
Yeah, but in polymatroids.
In polymatroids, good question. Yes. Let me think. I think. Yes. Yeah. No, you can also have the weak form. I just wrote you will see from the other definition that yeah, you could just stay with the weak form. It's
Thank you.
It's fine. Yeah.
Thank you.
Okay. So all right. So now let's look at the second definition and how it compares from the matrix setting to the polymatrix setting. So we are going to relax the definition here. In the matrix case, your bases were represented by points with 0, 1 coordinates. Now we have coordinates that are in Z. But essentially, this is the only difference. A polymetrid can be identified with polytopes in RE with integer vertices, such that the edge directions are of the form EI minus EJ, where these are again the canonical basis elements. So do you have some examples? So some examples here in 3D. Here you have the simplices or the permutohedra or associaedra here are represented. So these are called generalized permutohedra. These are the polytopes, which such as the edges direction are of this this form. And here there is a little difference with the matrix setting, which is that in the matrix setting, all the bases are vertices of the associated polytop. But for polymatroids, you see you have interior points. So you have some of your bases are, so the bases are really all the lattice points within your polytope. So you know, yeah. So yeah. So that's the correspondence. If you are given such a polytope, then the associated polymatroid is the set of integer points inside this polytope. And there is a way to describe these polytopes, this generalized permutohedra, in terms of the facets instead of the edges, and they are the polytopes whose facets are given by these inequalities. So the same type of inequality, sum of xi is less than a certain value, with equality when you take the sum of all coordinates, and the values here in the right hand side have to okay, so they can be taken as a submarilla function, and if you impose that it's a submarilla function, then it's unique and it's called the rank function. Okay, any question on this? Any additional question on this definition? So it's a very natural relaxation. So here we are going from sets to multisets. Here we are just allowing the vertices to, you know, be in Z to the E instead of 0, 1 to the E. And here we are, yeah, same thing. We are just allowing our rank function to, you know, to increase by more than 1 for singleton. Okay. All right, so now let me also motivate these definitions of polymatroid in terms of hypergraphs as an abstraction of hypergraphs. So what you are probably familiar with is that matroids are abstractions of graphs in a certain way, and I will see that polymatroids are abstractions of hypergraphs in the same way. So first, let me just state this fact for matroids. So if you have a connected graph G, the set of spanning trees form a matroid. Okay, so the matroids that I wrote earlier in this talk on 1, 2, 3, 4, 5 is actually correspond actually to a graph. Is formed in this manner. It's correspond to the set of spanning trees of this graph. So there are 8 spanning trees that gives these 8 bases. Okay, so now I want to kind of reproduce this type of motivation for polymatroids. So I need a notion of spanning trees for hypergraphs. Okay, so a hypergraph for me will be a set of vertices and a set of subsets of vertices. Or, you know, I will have hyperedges, and these hyperedges contain a certain number of vertices. So here you have an example with 4 hyperedges, and these hyperedges contain 2 vertices, and so on. Of course, we know that we can identify graphs with the hypergraphs such that every hyperedge has size 2 or 1 if you are allowing edges, allowing loops. And now I want to find a definition of hypertrees that will replace the notion of spanning trees. And I want this definition to be a generalization. That's to coincide in this special case of graphs. So here's the definition. I'm considering a hypergraph H, and as in the previous picture, I'm going to represent that by a bipartite graph BH. So here is my hypergraph that is represented by this bipartite graph here. On top, you have the hyperedges, and on the bottom you have the vertices. So I want to give a definition of a spanning hypertree. So a spanning tree of these 4 hypergraphs. So a spanning hypertree of H will be a points with coordinates indexed by the hyperedges, for which there exists a spanning tree of the bipartite graph, such that the coordinates of this point give the degree of the tree -1. There is just a conventional shift of 1 here. So for instance, for this, let me walk through this example. Here I'm looking at this hypergraph, and I'm claiming it has 3 hypertrees, namely 2, 0, 1, 1, and 0, 2. And okay, so how do I see that? So here is a bunch of spanning trees of the bipartite graph. And for a given spanning tree, I look at the degree of the tree at each of the hyperedges. So here the degree is 3, and here the degree is 1. So I subtract 1, so I get 2 and 0. And that gives me 1 of the hypertree. So this 2, 0 correspond to this situation. And there are other trees that will give me this same hypertree 2, 0. So I'm in the hypertree, I'm only recording this information 2, 0. 1, 1 could be obtained in this manner, and 0, 2 could be obtained in this manner. So these are definitely 3 of the hypertrees of H, and you can check that there are no others. Okay, so how should you think about this number? Okay, so if I look just at the number 2 and 0, what this says is that here I'm going to use this hyperedge to create 2 connections between vertices. And here, this 0 tells me I'm going to use this hyperedge will create no connection at all between the vertices. Here, I'm going to use this in this second example, it's 1 and 1, and that corresponds to the fact that I'm going to use this hyperedge to create 1 connection, and this hyperedge to create 1 connection, and so on. So that's a way of thinking about these numbers. And the remark is that if the hypergraph corresponds to a graph, meaning that each hyperedge is just of degree 2, then the spanning hypertrees of H are in bijection with the spanning trees of G. The correspondence is, if you have a 1, it means you are creating this connection between the 2 vertices. And if you have a 0, it means you are not creating a connection. You have a dangling edge that serves no purpose in terms of connecting the vertices. So you can convince yourself that the spanning hypertree of H are in bijection with what we would call the spanning trees of G. So the spanning hypertrees would just be the indicator vector of these spanning trees. I hope that makes sense. Is there any question on this?
Can I ask a question?
Yes.
Yeah. So you could have taken the degrees on V as well, right? And subtracted 1 and gotten the vectors 0, 0, 1, 0, 1, 0, and 1, 0, 0.
Yeah.
So like you could have.
Yeah. So I could have done some different some different information recording. So different information. Okay. So first of all, indeed there is a break of symmetry in this bipartite representation. So I'm saying which one are the hyperedges and which one are the vertices. So here in my definition, I'm only going to look at the degrees on the hyperedges.
Okay.
Great. So otherwise it correspond to the other hypergraph, and then I would have a different set of hypertrees. Yeah.
I see. So thanks.
And yes, again, yeah, so in terms of having that being a generalization of what happens for edges, for graphs, you know, what we want to know is, you know, which edges are in my spanning tree. And here I'm saying which edges, which hyper edges are in my tree, but also which multiplicity. Okay, so that's kind of this analog, and it coincides for graphs. Okay, so that kind of motivates, you know, this definition, this notion of okay, it motivates if I tell you the proposition that if you have a hypergraph H, the set of spanning hypertrees form a polymatroid. Okay, so here in this example, it's just in dimension 2 because I have only 2 hyper edges. So my polymatroid is just of dimension 2. Is this very simple thing? It has 3 lattice points, and it's this line segment here from 2, 0 to 0, 2. Okay, so all right, for any hypergraph, if you look at the set of spanning hypertrees, they satisfy this exchange axiom and therefore form a polymatroid. And there is something to say about. Okay, I'm going to do an additional remark about, you know, the space of polymatroid and how it compared to the space of hypergraphs. So first of all, there is a natural way of parametrizing the set of all polymatroids. So let's say I fix my ground set to be 1 to n, and I look at all polynomial on this ground set. Of course, there are infinitely many of them. I can encode them by a point in the space r to the 2n minus 1, 2 to the n minus 1, by associating to a polymatroid the value of the rank function. So the rank function, I have to specify the value for every set that is non-empty. So that's why I get this number of coordinates. And okay, and then that's, as we said, there is a unique rank function for each polymatroid, and conversely, any submodular function will give you a polymatroid. So actually, this set of polymatroid will be, you know, parameterized by the set of integer point here in this space, where that are given by these inequalities on the coordinates, the submodularity. So this is an infinite polydra which is fully dimensional, full dimension. So it has that dimension. Okay, the one remark that I want to make is that you know, the graphs are very special types of matroids. But hypergraphs are kind of representative of polymatroids in the sense that if you look at the set of polymatroids that comes from hypergraphs, that contains a full dimensional infinite cone. So in some sense, there is a positive fraction of, in some vague sense, for positive fraction of polymatroids that come from hypergraphs, which is a very different situation than for graphs. Okay. All right. I'm going to stop there with this vague motivation. So now, I mean, at this point where, you know, I have explained this natural generalization of matroids, and now I want to extend this matroid invariant, the Tutte polynomial, to the polymatroid setting. So what's the definition of the Tutte polynomial for matroid M? I'm recalling this definition of the Tutte polynomial. It's defined as the sum over all subset of the ground set of x minus 1 to the corank, y minus 1 to the nullity. where the current and the nullity of a subset are defined as follows. The recurrent is the number of elements to add in to your subset S in order to contain a basis of the Matroid. And the nullity is the number of elements you need to delete to your subset in order to be contained in a basis of your Matroid. So as an example here, if I take the matrix that is associated to this graph, I would have to look at all the subset of edges. And for each subset of edges S, I would get a certain contribution, which is x minus 1 to a certain power, y minus 1 to a certain power, which is given in terms of this current and nullity. So if you sum them all for this example, you would get this expression here. Okay. Going a little bit faster, one of the motivation for this Tutte polynomial is that it contains a lot of information about the graph or the matroid that it is associated to. So in this case of graphs, you can see that the Tutte polynomial contains information of subgraphs. So for instance, you would be able to deduce the number of spanning trees, the number of forests or connected subgraphs. But you can get also things about orientations, about colorings, some other statistical mechanics types of partition function. And so that's why it's an important and well-studied invariant. And one way to understand that it satisfies all of that, or that it contains so much information, is that it's universal among invariants satisfying dilation contraction formulas. By that, I mean a formula of this type, where the invariant of M would be expressed in terms of the invariant of M deleted I and M contracted I, when I is an element, any element that is neither loop or coloop, or if it's a loop, you would be expressed in this way or coloop in this way. So the Tutte polynomial satisfies such a relation with coefficients that are given here. But the universality property is that any invariant that satisfies such a relation can be obtained as a specialization of the Tutte polynomial. And if you think about it, it's kind of miraculous that such an invariant exists, because here, you know, this relation should hold no matter which elements I you start with. So you can apply this deletion contraction rules in any order, and it's supposed to give you the same value at the end, which is quite miraculous, really. And related to this, I mean, when Tutte first defined his polynomial, what he wanted is just something that satisfies that. So he defined it in this manner, as the sum over basis instead. So without knowing an explicit expression, like a more straightforward expression, he gave this definition. First, fix a total order on the ground set. That would be the order in which you do your deletion contraction. And then the Tutte polynomial defined by Tutte is defined it as the sum over all bases of your matroid, x to the number of internally active edges, y to the number of externally active edges. So now let me explain what this means. So you have two sets here: the internally active elements for a given basis and the externally active elements for this basis. So let me take a basis of my matroid, and I want to tell you which elements are active or not. So I'm going to say that an element of A of the basis is internally active, it's in this set, if it cannot be replaced by a smaller element, meaning you cannot delete I and add back a smaller j and get a basis. So in that case, we say that I is internally active, we put it in that set. there is this dual notion of externally active elements. These are the elements that are not in the basis, but cannot replace a smaller element. There is no j less than I, such that I would add I and remove j and get a basis. So as an example here, if I look at the matroid that correspond to this graph and the basis that is this spanning tree. So I'm saying that 1 is internally active because it is an element of T that cannot be replaced by a smaller element. There is no smaller element anyway. 5 is not active though, because I could remove 5 and replace it by a smaller element, for instance, 2. So 5 is not in the set, and 4, similarly, it could be replaced by a smaller element, namely 3. So it's not active either. So the internally active elements are just 1. For the external edges now, I look at the elements 2, but that 2 can replace a smaller element, namely 1. So it's not active. 3, however, cannot replace a smaller element. It can only replace 4 or 5, and therefore it cannot replace a smaller element, so it's active. So I get 3 in that set. All right, so now I'll going back to that definition, that theorem. The theorem says that if you sum over all bases this contribution x to the number of internally active elements and y to the number of externally active elements, you get the Tutte polynomial. So that's a new expression for the Tutte polynomial. Here is an example here where I've done this computation, and you get the same expression as before. So this expression is very miraculous because the contribution of each individual basis is going to depend on the total order, because these sets here depends on the total order that I put on E. But the theorem says that when you sum over all bases, then the result does not depend on this total order. It's equal to the Tutte polynomial. Okay, so this is very miraculous, and one way to prove that is to just prove the two expressions are equal. So you have one expression in terms of activity of basis, and one in terms of corank and nullity of subgraphs. I want to prove that the two sum are equal, and the relation was discovered by Crapo, and it says that you can group the subgraph in some certain way, in such a way that a bunch of subgraph is going to have the same contribution as this basis, in terms of activity here and in terms of corank nullity here. So precisely, if you take a basis and you look at the active elements, you can look at all the subset that can be obtained from this basis by flipping the active elements, meaning that for the active element, you can choose to add them or delete them freely. So from this basis, for instance, you would get this set of subgraphs. From this basis, you would get this set of subgraph, and for this basis, you would get this set of subgraph. And the result is that it's very beautiful. It's that from these interval associated to each basis, they form a partition of the Boolean lattice of subgraphs. And moreover, the contributions coincide, meaning that if this spanning tree was contributing a certain contribution in the expression, this set of subgraph contribute the same. So here x squared for this one, and x for this, and y for this. So I'm not telling you why that's true, but this is a very beautiful fact that relates the two formula for the Tutte polynomial. Okay. All right. So now let me explain how to move to the polymatroid setting. So there is we are trying to find analog of this definition that would make sense. So I'm going to try to define an analog of the activity definition. So let's take P a polymatroid, and for an element, a basis of P, I want to define some sets of active elements. So a natural definition for internally active would be an index I of the ground set such that there is that cannot be replaced by a smaller element again. So in the sense that you cannot decrease the value, the coordinate in I, and increase the value, the coordinate in J, and stay in P. So if this is the case, if you cannot replace, in decrement I and increment a smaller J, then you say that you are active for it. And similarly for the externally active, you say that I is externally active. If it cannot be, you cannot increase I while decreasing a smaller J. And then the natural, you may want to define your Tutte polynomial in this manner. Okay. So just let's look at the geometric meaning of these activities here to get a little bit of a better sense of what they mean. So here is a polymatroid, and here are all the bases, like each point is a basis. And for a basis, I want to know what are the internally active edges and externally active edges. So one is always active, because there is never something smaller than one. Then if I look at 2, what does it mean? I shouldn't be able to move in the direction 2 minus 2 plus 1. So it means that I'm internally active if looking at this place, I'm not in the polymatroid. Okay, so if in this direction, if this direction is outside of the polymatroid, then that means 2 is internally active. For 3 to be internally active, you would need to check that there is nobody in that direction and nobody in that direction. That would mean that that 3 is internally active. So for instance, for this point, you can check that 1 and 2 are internally active and 1, 2, 3 are externally active. Okay. All right, but okay, so that's a good dream, but it doesn't work. So the problem with that definition is that this is dependent on the ordering of n, meaning that if you permute n, your polymatroids should be the same. If you have just it's a isomorphic polymatroid, but this sum is changed. So you don't get the miracle you had for matroids, that while the contributions are dependent on the order, the sum was not dependent on the order. But here, yeah, this miracle does not happen.
So Oliver, so we have 10 minutes left. So I see you have 68 slides. So just a reminder of the time.
Yes. So, okay. Yeah. Somehow. Okay. That's good. That's good that you remind me. Yeah. So let me say. I'm not going to say everything, but let me say a little bit more here. So here, the thing is, it didn't work, but there are 2 things that did work, which was if you specialize one of the variable to 1, then the sum became invariant. So in some sense, this definition was not good, but it was close to be good. So, and one of the proof to show that these specializations were indeed invariant according to reordering of n is that they were equivalent to some kind of hierarchical polynomial, which were independent of the ordering. They were just polynomials that were counting points in P plus Q times the Q dilation of the simplex. So this is a type of paired polynomial. It's a polynomial in Q, and it contains the same information as TP of x1. And same thing for 1y, but with the inverted simplex. So what Cameron and Fink did is, okay, all right, this definition doesn't work, but why not take that as a definition? And so what they did is they looked at this polynomial that corresponds to the AR polynomial of, you look at the number of lattice points in P plus K times the K times the inverted simplex and L times the simplex. And you look at this as a polynomial in K and L. And this gives you an invariant of your polymatroid. And what they proved is that this was a fair generalization of the Tutte polynomial matroid, because in the case of matroid, it contained the same information as the Tutte polynomial. So, however, it didn't really, give analogs of the subgraph expansion of the Tutte polynomial or the basis expansion of the Tutte polynomial. So that's what we wanted to do. So here is the fix. All right, so the right definition is the following. So you define the activities as before, but you define the contribution in a slightly modified manner. Before, in the previous attempt, an element I that was both internally and externally active, it would contribute x, y. And now, instead, we make them contribute x plus y minus 1. All right. And all right, so you do that. And in this, with this, this is a correct definition in the sense that this polynomial is indeed invariant under reordering of A. It's a true invariant of your polymatroid. Does not depend on the order that you put on the ground set. And it's also a legitimate generalization of the Tutte polynomial. There is a little change of variable because actually the notion of activities that I've put here are, they look the same, but they are not exactly the same as the one I have used for matroids, but they are related by just a technical factor. So you get a technical change of variable, but it's otherwise the same invariant up to this change of variable. So all right, that's good. So that means that we can extend the activity definition of the Tutte polynomial to the polymatroid setting. But we want also maybe a current nullity formula. But the current nullity formula now is not going to be as a sum over subsets. It has to be a sum over all the points in Z to the E. So, and it works. Once you have this fix, you can find an expression that works well. The Tutte polynomial of your polymatroid can be defined in terms in terms of the sum over all points of Zn due to the corank V to the nullity, where the corank is again how much you need to add in order to contain a basis, and the nullity is how much you need to subtract in order to be contained in a basis. Okay, so you have a very natural extension, except now you are summing over Z to the N, and therefore you get a series, and there you have to interpret these two as series in U and V. And the reason for these two competing definition is again some kind of interval partition. So there is this analog of the proper partition, but now we are going to do it over the full space instead of 0, 1 to the n. So for that, you need to define an interval for each basis, or here it's going to be some kind of octant or half-plane or whatever. Let me show a picture. So here's a polymatroid, and to each basis, I'm going to associate a cone centered at that point and that cover. So these are actually 2 times the same picture. Just that here the one direction is perpendicular to the board on the second picture. And okay, so according to the set of internally active elements or externally active elements, you get rays in the positive direction, negative direction, or both directions. Okay, and you like that associate a cone to each element of your basis, and the claim is that this form a proper partition of the lattice D to the n, and that the contribution of this set of points associated to your basis is the contribution of your basis, if you replace x and y by 1 over 1 minus u or 1 over 1 minus v. Okay. All right, so that's for the 2 definitions, and that it works well. It's equivalent to the Cameron-Fink invariant that I mentioned earlier, this Hart-type invariant. And it satisfies some of the properties of the Tutte polynomial, like duality is property that generalizes well. There is a nice way to understand the Brilowski identity at that level that is much more natural than at the Matroid level. That is has some nice other properties that I'm going to skip. So let me, since I'm running out of time, let me just say what this other part that I've not presented is about. As I said, it is about showing that the Tutte polynomial is naturally a polynomial function of the rank function values. A precise way to say that is that for an integer n, you look at the polymatroids on 1 to n, and the Tutte polynomial of these polymatroids can be obtained from a single universal polynomial Tn by plugging the values of the rank function. Okay, so this universal Tutte polynomial has the 2 normal variables x and y, and then the bunch of variables that correspond to that are going to be set to the value of the rank function to give the Tutte polynomial of your particular polymatroids. So for instance, for n equal to 3, the expression for the universal polynomial T3 is the following. Okay. And yeah, so let me skip and say that not only we have this polynomial result, which is already a strong tool in itself, but we also have an explicit expression. I'm not going to go over the expression, but it's explicit in terms of a finite sum. It is something like that, where this polynomial, these dragon polynomials are defined in a combinatorial way. So you have to sum over set partitions, and you get certain activities that are going to be okay. Anyway, I'm not going to read this formula. It's a little bit too much to chew for this remaining minute. But I wanted to say that the expression is explicit and sufficiently explicit that you can specialize it for instance, zonotops. And as an example, here is the expression for the polymatroid, which is the permutahedron. So you get some combinatorial expression in this manner. Okay, and I'm going to stop here.
Thanks a lot, Olivier. Let's thank the speaker. Any questions for the speaker?
What about a deletion contraction formula? Do you have one of those?
We wish. No, we can only get them for very special cases. I mean, if your polymatroid is very flat in one direction, like one or two levels, then yes. Otherwise, we cannot. We don't know how to do it. That's certainly something. I mean, in some sense, you know, this the fact that there is an expression in terms of activities lets you get some hope that there would be something like that, but we haven't been able to figure it out, and we don't know if there is one.
Okay, thank you.
I have a question. So would it make sense? I mean, this is hard enough already, but would it make sense to add simplices that aren't the opposite hypersimplex and the standard simplex, like hypersimplices in between? In this Cameron-Fink setup, you'll probably get more variables, but is it anything worthwhile or too complicated?
So I guess we don't have a strong motivation to look in that direction. You know, in the sense that yeah, this was meant to kind of solve this issue of defining, capturing enough information on the polytop that it would give you the same information at the Tutte polynomial. And now, yeah, you could look at additional things. So we didn't look there. There is one interesting thing, though, that in a little bit in that direction, which is, you know, you can do mixed volume with this hierarchy theory, meaning look, take two polytops and look at linear combinations. You know, linear combination in the sense of Minkowski's sum. So you look at the sum of two dilations, and this you look at that as a two-variable polynomial. Okay, so there is this notion of mixed volume or mixed hierarchy polynomial here. But one thing that comes out of the polynomiality is that it's a little bit more than the hierarchy polynomial that you can do. You can look at the polynomial of these linear combinations, and this is going to be polynomial in the parameters of the dilations. So it's kind of yeah. So it's that's quite of kind of interesting, and we are not sure, you know. Yeah. So this is kind of something to explore somehow, and we haven't.
I also have a question. Like, is there any hope maybe that using like your methods, like I don't know, like maybe playing with universal Tutte polynomial, it could be possible to obtain, like, say, description of Newton polygons of Tutte polynomials, or somehow like maybe related with the huge variety of polytops arising in your story?
So I don't know precisely for the direction you are suggesting. What I would say is that it's possible. I mean, one of the hope here is that the Matroids are very complicated in terms of, you know, if you compare them to normal polymatroids, they are kind of the worst. Like they are very far from generic. So here's a kind of a generic picture of a polymatroid in dimension 3, where all the facets are there. But the Matroids are the worst. They are like very degenerate. So in terms of the space of polymatroids, they sit very much at, you know, at very low level faces. The low dimensional faces. What there is a hope that things are actually better behaved in the bulk, and you can get formulas in the bulk with less work, because things are nice there. And in particular, it's, for instance, if you want a polynomial relation, it's sufficient to you can focus on just hypergraphs. inside that block, and maybe there are relations there that you can get, and then it extends polynomially, so it extends to these degenerate cases that are matroids. So yes, that's kind of one hope that maybe things are especially hard to prove in the matroid settings, but less so in the bulk of the polymatroid space.
Yeah, thanks.
Any other questions? So I had a question that you, partly already answered, that how the matroidal rank function sits inside the rank function of all polymatroids.
Mm-hmm.
Another question is, how does, so you have in the beginning, you defined hypertrees for the matroids. How does the dual of a matroid, the hypertree of the dual of a matroid looks like?
Yes, so yes, I mentioned duality very fast, but let me go back on what we mean by the dual of a polymatroid. So if you think about a matroid as a set of points in 0, 1 to the e, what is the dual? Well, it's you have to you have to flip your matroid. The 1 becomes 0 and 0 becomes 1. So what you do is you take minus your polytop and then put it back in the 0, 1 place. So for a polymatroid P, we can define the dual as minus P. Anyways, so everything we look at in terms of polymatroid is invariant under translation. So our invariance, all our theory is invariant under translation also, on top of permutation. So anyway, so the correct notion of duality for polymatroid is minus P. Yes, and then it reverses this. The notion of internal activity becomes external activity, and so on. Does that answer your question?
Okay, yeah. And one last thing, so do we, so because you mentioned the Fink-Cameron type polynomial,
mm-hmm.
where they shift the polytope by a like hypersimplex,
mm-hmm.
of like reverse hypersimplex,
mm-hmm.
or simplex just. So how does this generalized or the universal type polynomial can also be gotten by adding a shift of some other polytope to the polymatroid?
So yeah, so that's similar to Vasu's question, like are the simplices and inverse simplex special? I mean, they get the work done in terms of these activities. I mean, the relation here is becomes let me see. Here's the relation between the two. So here is the Cameron-Fink invariance. So this is the Erhard polynomial when you add dilations of the simplex and the inverted simplex. And if you express, this polynomial, this Erhard polynomial in the following factorial basis, then the coefficients are the same as the coefficients of our Tutte polynomial. So they encode this internal external activity in some sense, and it plays very well with this cone partition of space. So if you look at this set of points that are in this P plus this dilation of simplex and cosimplex, you intersect that with the cone of a base, and you look at the contribution of these points inside the cone, I mean the number of points inside that cone, and that will give you, you know, the right contribution in terms of what this this thing corresponds. So it's a very close very well-behaved correspondence. Could we get an invariant that has the same information by, you know, taking two other polytop? I'm not 100% sure. I mean, but definitely this one is the natural one and in our setting. So I don't know.
Okay, thanks a lot. There's a question in the chat. So let us. So I'm gonna stop the recording, and